So we have studied the ideal diode analysis, right? So now let us look at the practical diode model analysis. Let us see how the practical diode will reshape the waveform. Okay, so the same negative clipper we will consider using practical diode model. Okay, in case of practical diode model, what are we going to consider? We are going to consider, so Vk needs to be considered. Okay, so let us draw the circuit diagram. Okay, and let us consider positive half cycle itself. Positive half cycle. So this is the source. For positive half cycle, upper side we will consider it as positive and lower side negative. And you have to place now a practical diode. How are you going to place the practical diode? Place an ideal diode first. Anode and cathode, and you can call it as ID. ID stands for ideal diode. And then you have to place this Vk. Vk is the barrier potential. You have to place the barrier potential in such a way that the barrier potential always opposes the diode conduction. So that means to say, positive terminal of Vk needs to be connected to the cathode terminal. Okay. And the negative terminal can be connected to the load resistor. Okay. Alright, and across RL we are going to measure the output voltage V0. Okay. Now, in case of practical diode model, as you can clearly observe that there are two sources in place, right? On the left hand side, you have an AC source, and on the right hand side, you have which source? A DC source. And why that DC source has come into existence? Because of the barrier potential. Okay, we do not know what is the value of Vk. It could be 0.7 for silicon or it could be 0.3 for germanium. That is not the question over here. The question over here is that how this Vk will affect the working of this negative clipper. Alright, now in this case, what you have to do is, first step is to look for source opposition. Okay, source opposition. Now, why source opposition? Since there are two sources, you have to check whether the two sources are opposing each other or are they helping each other. Okay, so that can be easily checked by looking into the direction in which the two sources are trying to circulate the current. Now, for Vs, you have assumed minus and plus polarity, right? In case of, this polarity convention, the current is considered in this direction, right? So your AC current is flowing in kind of clockwise direction, right? On the other hand, if you look at the DC source tries to circulate the current in the anti-clockwise direction. Okay, so AC source tries to circulate the current in the clockwise direction, and the DC source tries to circulate the current in anti-clockwise direction. So if you look at the two current directions, you see that two sources are opposing each other. The two sources are opposing each other. Now the question is, which source is dominating? The dominating source will dictate the circuit operation. Okay. Now, in order to understand the source domination, what you have to understand is that the magnitude of Vk, let me write Vk, magnitude of Vk is fixed. 0.7 volt for silicon, 0.3 volt for germanium. On the other hand, the magnitude of Vs is not fixed because Vs is a sinusoidal source. So Vs can assume infinite instantaneous values. Your Vs for a positive half cycle, it can be at 0 volt level, it can be at 0.1 volt level, 0.2 volt level, and it will rise up to plus Vm, and then again it falls to 0 volt level. So your Vs is a continuous source, hence you have to break down your positive half cycle analysis into two parts. The first part, let us call it as case A. So in first case, what we can consider is that what if the source voltage is less than Vk. So that means to say there can be a time instant in which the source voltage can be less than Vk, right? For example, if you were to compare an instantaneous value of 0.1 volt of Vs with 0.7 volt of Vk, you can clearly say that the potential of Vk is greater than source voltage. So in this case, which source is going to dominate? Obviously Vk, because Vk has more potential. So whenever Vs is less than Vk, you can say that Vk. Okay. And what's the meaning of dominating source? The meaning of dominating source is that the working of the circuit is dominated by this Vk source. And how this Vk source is trying to circulate the current? The Vk source is trying to circulate the current in the anti-clockwise direction, and you can clearly observe that the positive terminal of Vk is connected to cathode terminal. Since Vk is dominating, you can say that diode gets reverse biased. Diode gets reverse biased. So in this case, the equivalent circuit looks something like this. Though we are in the positive half cycle, due to the dominating nature of Vk, the diode is driven into reverse biasing mode. So what do you mean by reverse biasing mode? No conduction. So there is an open circuit situation exists between anode and cathode terminal, and this is your Vk plus minus Vk, and this is your load resistor RL, and this is your V0 minus and plus terminal. Okay, since diode is reverse biased, you can say that current is 0 amperes, because in an open circuit situation, the current becomes 0 amperes, and therefore your output voltage, which is measured across RL, which is nothing but I into RL, Ohm's law, so which is 0 volt. So as long as your input is less than the barrier potential, your diode will be in off state. Now let us take the situation which we can consider it as case B. Okay. What if the input voltage Vs is greater than Vk? As I was mentioning that your input voltage is a sinusoidal signal, right? So it can assume 0 volt value, it can assume even small values such as 0.1 volt, okay, and it can also assume the unique plus Vm value as well. So it has multiple, in fact, infinite instantaneous values. So what if those instantaneous values are greater than Vk? Okay, so whenever your Vs is greater than Vk, you can say that Vs is dominating simply because Vs has more potential to circulate the current. Okay, if that is the case, what happens to diode conduction? So which is more dominating in case B? Vs is greater than Vk, hence Vs is dominating. So the current circulated in the circuit should be in accordance with the polarity of Vs. And you can clearly observe that whenever Vs becomes dominating in nature, you can trace that the Vs is connected to the anode terminal of the diode. Hence, Vs forward biases the diode. Okay. So in this case, the equivalent circuit looks something like this. This is your Vs. The diode is forward biased, hence it can be replaced with a short circuit equivalent. Then comes Vk, and then comes the load resistor RL. Across the load resistor, you're going to observe the output voltage minus plus Vs, right? So Vs is going to forward bias the diode, and you can clearly observe that the circuit is closed now. Okay. So all what you can do is you can apply KVL in this case. Okay. Apply KVL in the clockwise direction, okay, or along the direction of current I. So start collecting the polarities. Minus to plus, plus Vs, then plus to minus, minus Vk, then plus to minus, minus V0 is equal to 0, or your output voltage V0 is equal to source voltage Vs minus Vk. Okay. So what you have to understand over here is that in case of ideal diode analysis, for the positive half cycle, we had obtained V0 is equal to Vs. On the other hand, for a practical diode model, we have obtained V0 is equal to Vs minus Vk. And so what is happening is this barrier potential is slightly limiting the output voltage. Okay. So the output voltage, is limited by this Vk factor. Okay. So this is your equation for output voltage. Right. So during positive half cycle, and during negative half cycle, you can swap the polarity of the source, upper side negative, lower side positive. Okay. Yeah, so this is your diode, anode, cathode. Load resistor RL, V0, polarity for Vk you have to put. Now, for the negative half cycle, you can once again check for the source dominance. Obviously, you can clearly observe that here Vs is trying to circulate the current in the anti-clockwise direction because minus to plus, and your Vk is also trying to circulate the current in anti-clockwise direction. So basically, Vs and Vk are helping each other in reverse biasing the diode, right? So another way of looking at the things is by observing this. Negative terminal is connected to anode, correct, on one side. So on the other side, you can also see that the positive terminal of Vk is connected to cathode. So Vs and Vk, they are trying to circulate the current in the anti-clockwise direction. In that process, they basically reverse bias the diode D. Okay, so in case of the negative half cycle, the diode stays in reverse biasing mode. So diode stays in reverse biasing mode for the entire negative half cycle. Okay, so the equivalent circuit is going to be something like this. Open circuit across the diode terminal, anode and cathode. Source voltage Vs, V0, okay, so I is equal to 0 because the diode stays in reverse biasing mode, and therefore V0 is equal to, I into RL is equal to 0 into RL. So output is still at 0 volt level. Okay, so this is the analysis of a negative series clipper with a practical diode. So now let us plot the input and output waveforms. Now you can observe how Vk is reshaping the output waveform. So this is your input. Right below the input, you can sketch output. Okay. So input is a bidirectional signal, sinusoidal signal. Just drop the projection line onto the x-axis towards V0. So that will help you in sketching the positive half cycle of the output as well as negative half cycle of the output. Okay. You had observed that during the positive half cycle of the input waveform, the barrier potential was contributing something known as source dominance, right? So the barrier potential was opposing the diode conduction for the positive half cycle of the input. Therefore, what we will do is we will mark the barrier potential level in the positive half cycle. Okay. So this is your Vk level. Vk level. Okay. So this is your intersection point with the input waveform. So what you do is from those intersection points, you draw the projection line towards the output as well. See, the barrier potential was affecting the positive half cycle of the input. That's why we have projected along the positive half cycle. If it were to, affect the negative half cycle of the input waveform, then we would have projected along the negative half cycle. So that you will understand in the future topics. All right. Now, during the positive half cycle, there were two cases. Vs less than Vk and Vs greater than Vk. So as long as the input is less than Vk, what was the output? Output was 0 volt level. Let me use a different color. Probably. Yeah. So this is the region in which input was less than Vk. Let me write here. So here Vs was less than Vk. So this blue line indicates that your source voltage is less than Vk. So when your source voltage was less than Vk, you had obtained output is equal to 0 volt, right? So in this particular region, your output is at 0 volt level. Similarly, you have the same region in the downgoing side of the positive half cycle. So even in this region, your output was, so this was your Kz, let me write here. This was your Kz, wherein your source voltage was less than Vk. Then you had the second case in which your source voltage was dominating the barrier potential Vk. So during that case, you had obtained your output V naught is equal to Vs minus Vk. And this is case B. Right. So that means to say this one. But when your input is greater than Vk, your output is Vs minus Vk. So that means to say this shaded region, which is marked in pink color, should be drawn in the output waveform. So this shaded pink region should be redrawn here. So when your input reaches plus Vm, so here let me write. So when Vs reaches Vm, what will be the value of V naught? V naught going to be Vm minus Vk. Example, if you consider a silicon diode and if at all, let's say the amplitude of the source signal is 5 volts, then your output amplitude going to be 5 minus 0.7, which is 4.3 volts. In case of ideal diode analysis, you had observed that during positive half cycle of the input, your output was always at Vm level, right? V naught is equal to Vs. In case of practical diode analysis, you are getting a slightly different equation in which output V naught is equal to Vs minus Vk. So your output is always less than the input by Vk level. For a silicon diode, it is 0.7. And if you assume Vm is equal to 5, you know how much amplitude you are going to get? You are going to get an amplitude of 4.3 volts. So that's how the Vk, reshape the output waveform. So when your input is at Vm, your output will be at Vm minus Vk. Okay. And for negative half cycle, you had observed that for the entire negative half cycle, the output was 0 volts. Entire negative half cycle, output is at 0 volt level. And after this, you can draw the transfer characteristics. I'll draw the transfer characteristics here as well. Plus Vi minus Vi plus V naught minus V naught. Okay. See, you need not find out the slope every now and then. Okay. So basically, you can plot the transfer characteristics from your input-output waveform itself. Okay. So in your waveform, you had seen that Vk is affecting the positive half cycle, right? So what you have to do is, this is your positive half cycle. Positive half cycle of the input. So you have to mark Vk along the positive half cycle. Okay, so let us assume that this is the Vk level. Okay, and this is the maximum value of the input. Okay. And if you see your output stays at 0 volt level as long as your input is less than Vk. So what you can do is, you can mark that same length along the y-axis as well. Okay. And you can also mark this particular limit, that is Vs minus V. So that is somewhere over here. Okay. Now, as long as your input is less than Vk, output is 0. Right? As long as your input is less than Vk, output is 0 volt. So how do you represent 0 volt level? line parallel to the x-axis. Okay. Once your input starts to exceed the Vk level, that is, whenever Vs is greater than Vk, you will get V naught is equal to Vs minus Vk, so which is basically AC signal, right? So because Vs is an AC signal, so whenever Vs is greater than Vk, your output going to be an AC signal. So in that case, straight. Okay, and the maximum value of the output is Vm minus Vk. And for the negative half cycle, your output is 0 volt. So line parallel to negative x-axis. At this point, you can write it as. So this is the transfer characteristics. So your transfer characteristics in case of practical diode case is getting shifted by Vk level. Okay, so this is what you have to understand. Okay, in case of ideal diode analysis, you have observed that it was starting right from the origin. Okay, so this is for ideal. The yellow line stands for ideal, and this white line stands for. So this is how the barrier potential reshapes the waveform. Okay, yeah, that's it for the today.